So this unit has a couple chunks to it: pressure, density, pressure at depth. Those collectively combine for like a chunk. The second chunk is going to be on buoyancy. So we're going to introduce buoyancy. We're going to start working on a problem today from that in-class sheet. We aren't going to finish it just because it's going to take more time than I kind of want to devote to it today. I want to kind of introduce it. I want to get us thinking about it. I want to get us started on it. But then we're gonna pause on buoyancy and kind of wrap up that last chunk. So we'll get started. We'll talk a little bit about buoyancy. Then we're gonna go through, and I have a progress quiz for you. And then from the progress quiz, when you finish that and check your answers, then you'll have a little bit of time at the end to make sure you have some time to ask any final questions on the homework sheet called pressure, density, and pressure at depth. That's due this Sunday. So to get any of those kind of taken care of. So when we talk about buoyancy is something when we typically talk about it when something is in like water. Buoyancy is a force, and it's a force that exists anytime an object is immersed in a fluid. Anytime an object is immersed in a fluid, there is a buoyant force. And that buoyant force is always going to be upwards. So when we talk about buoyant forces, we're going to draw free body diagrams. It's a force. When we talk about buoyant forces, we're going to use Newton's second law because it's a force. So with free body diagrams, we build Newton's second law equation and we can solve for some things. The most common example of buoyant forces is things in water. Whether they are sitting at the bottom of a pool, there's still a buoyant force, or if they're floating on a surface, there's a buoyant force. The reason you can pick up your friend easier in the pool than you can walking down the hallway is because there's an upward buoyant force that is also picking upward on your friend when you're in the pool that helps you pick them up. Now, I'd be lying to you if I say that it only is true in water, because anytime an object is immersed in a fluid, there's a buoyant force, which right now you are immersed in a fluid. The fluid is called air. So right now you do have a buoyant force acting on you. It's a very small buoyant force, and in fact it tends to be so small that we just immediately ignore it. But officially there's a buoyant force. So when you step on a scale, you are actually a tiny bit heavier than the scale says because the air around us is actually picking us upwards. So if you were to stand on a scale in a perfect vacuum, where there is no air, compared to in the room, your scale would be slightly different. There's some physical issues with you standing in perfect vacuum in terms of like living and stuff like that, but there is a buoyant force. We tend to ignore buoyant force in the air most of the time, but there are some times we do care. Like with a helium balloon, that buoyant force is what causes that balloon full of helium to lift upwards into the air. Okay? But a buoyant force is always upwards. So with forces, which is measured in newtons, we're going to have to talk about free body diagrams and Newton's second law. So Newton's second law is sum of all my forces equal to F net, which is equal to mass times acceleration. But when we talk about buoyant forces are an upward force. So my free body diagrams, my arrow is going to be pointing upwards. So when I talk about buoyant forces, what I'm really concerned about is I'm worried about my force in the y direction and really only the forces in my y direction. So a quick reminder that when we sum up my forces in the y direction, we add our ups, and we subtract our downs, and we set it equal to m times a. If my velocity is constant, then my acceleration, is it 0 or is it not equal to 0? Which one is it if my velocity is constant? If your velocity is constant, your acceleration is 0 or not zero? It's zero. Your acceleration is equal to zero. If your velocity is changing, then it's not equal to zero. So just some things to think about as we're talking about buoyancy. Couple kind of variations of buoyant force kind of problems. If I have a container of water, the water level is a little bit too high. If my water level of my tank looks something like that, my tank is empty. If I take something that's very dense and it's going to sink, and if I place that object in the bottom of my container, or if I climb in a bathtub, or if I jump in a lake, or if I put my boat in a boat landing, some of these are easier to see than others. What physically happens to my water level? Here's a bathtub, empty. You climb into the bathtub. What happens to the water level? It goes up. Why? Because you take up space. Yeah, you take up space, right? So that water level is going to go up a little bit. And this kind of leads us to something coming up here. But the idea is anytime an object is immersed in a fluid, they're going to displace a fluid. And they're going to push a certain amount of fluid out of the way. So when we talk about this object sitting on the bottom, how much of it is underneath the water? Well, all of it's underneath the water. So how much volume is displaced? Well, this entire block's volume is being displaced. So we could talk about forces here because it's sitting on the bottom of the container, there's a normal force. Because it's immersed in a fluid, there's a buoyant force. And because it's on Earth, there's a gravitational force. Or we could have a block on a string. There's a gravitational force, there's a buoyant force, and there's a tension. Or I have a block that's floating on the surface. There's a buoyant force. There's a gravitational force. Now there's a few other variations, but in terms of water, that's kind of where we're at. What's true about the velocity, is it constant or changing, of a block floating on the surface? Is it constant or changing if it's floating on the surface? Come on, help me out here. Object's floating on the surface. Is the velocity of that object constant or is it changing? Pretend there's no waves. It's constant, which means my acceleration would be zero. If this thing is being held in place, well, let's go over here. If a rock is sitting on the bottom of the lake, what's true about the velocity of that rock sitting on the bottom of the lake? Constant or changing? Which means my acceleration is zero. What if that rock has a rope tied around it and you're holding it somewhere between the surface and the bottom? What's true about the velocity of that rock? Constant. Acceleration is zero. For the most part, most of the time for us at least, not always in life, but we're going to deal with situations where it's sitting on the surface, it's sitting on the bottom, or it's being held somewhere in between, where the objects are not accelerated. So my acceleration is zero. Some variations could be an object is sinking, it's in the process of going to the bottom of the lake, then it is accelerating, but that's not what we're talking about. Those aren't the problems we are going to do. Okay? So when we talk about free body diagrams, that's something we got to keep in mind. Most of the time our acceleration is going to be zero, because my velocity of most of my situations are going to be zero. I think it's safe to say in all of our situations it's going to be like that. I think that's So, if we look at our equation, we have a buoyant force equation, and that's the equation we use very specifically to calculate this. And we talk about the buoyant force, there are three things in our equation, and the three things in our equation are density, volume, and gravitational acceleration. So density, volume, and gravitational acceleration. So when we talk about our density, we got to make sure we choose the right density. Okay? We got to make sure we choose the right density. So when we choose this density, it's like in a given problem, they'll talk about a block has a density of this and has a water is immersed in water that has a density of this. Okay? So in a situation like this, when we use it, it's the density that's being displaced. It's what is the density, what is the density that is being displaced? Okay, so what is the density of what's being displaced? Okay, that's fine. Okay, so when we talk about the density that's being displaced, is what is the density that's being displaced? So given a problem, I have a block that's floating on the surface. The block has a density of 500, and it's sitting in water that has a density of 1,000. What gets pushed out of the way? Does the water get pushed out of the way because of the block, or does the block get pushed out of the way because of the water? The water gets pushed out of the way. Most of the time, this is going to be the density of water. Mostly, it's going to be water. Not always. Like a helium balloon, there's no water when we talk about a helium balloon in the classroom. But most of the time, what's getting pushed out of the way when you put something in water is the water. If I were to put a piece of wood in salt water, then I'd have to use the density of salt water. If I put it in fresh water, I'd have to put the density of fresh water. So that's what that's really looking at. What is the density that is being displaced? What's getting pushed out of the way? Most of the time, that's going to be water. When we talk about this volume that's being displaced, what we're figuring out is how much, and I'm specifically talking about volume, is immersed. Is immersed have two M's or one M? I think it's two M's? That doesn't look right either. Is it immersed or E? No, is it with an I or an E? Man. Anybody? I'm terrible at spelling. Immersed. Two M's. Two M's. Thanks, everyone. Appreciate the help. Sorry, YouTube. My class let me down. I don't know. I didn't know how to spell it either. Just kidding, YouTube fans. Don't forget to like and subscribe, by the way. So how much volume is going to be immersed? And when I say immersed, I'm like underwater. Okay? And that volume needs to be measured in meters cubed times g, which is our gravitational acceleration. Okay? We're on Earth, so. So that's how we use our equation. Our equation is what is being displaced. So most of the time it's going to be water. Then you're going to put the density of water. How much water is being displaced, and really what that's equal to is how much of it is underneath the water. So in this situation, for that volume that's being displaced, it's the shaded region here in blue. It only be the volume of that object that's underneath the water. So it'd only be that much. In this object, because it's completely immersed, it would be the entire volume. Because this object is completely underwater, it would be the entire volume. So that's kind of where we're headed. If we take a look at question number 1A on the worksheet called In Class Buoyancy, that you should have picked up on the way in. We're going to start getting this set up. We're not going to finish it today, but we're going to get it started. So on that worksheet, there's two parts. We're going to do one part and only one part. So, a block with a density of 650 kilograms per cubic meter is floating in freshwater. The dimensions of the block are 0.25 meters long by 0.15 meters wide and 0.1 meters high. The density of water is 1,000 kilograms per cubic meter. How far below the surface will the block be? So, for number 1A, have a block, and with these blocks, 3 dimensions kind of is helpful, because it makes labeling it a little bit. I'm by no means a good 3-dimensional object drawer, but just to kind of get it in 3 dimensions is somewhat helpful. So the idea of the dimensions is this is 0.25 meters wide by 0.15 meters wide, long by wide, sorry, I think I screwed this up, by 0.1 meter high. I really don't care about where the 0.25 and the 0.15 go. Those two are the length times the width. My height needs to be the height though. That does matter. If you notice, my height looks way, this happens to be my smallest number, but in my picture it's the biggest, but whatever. Okay, now this block is floating on the surface. So because it's floating on the surface, I put a water level in to kind of show that. The question being asked is, how far underwater is it? How far is it from here to here? Okay. Just to make sure this is clear, from here to here is 0.1 meters. So, in order to solve for that h, we will have to use buoyancy. Specifically, it's going to come in when we talk about this volume being displaced. So when I solve for that h, the h is, this volume being displaced is how much volume is immersed. How much of it is underwater? And the idea of that is when I talk about that V being displaced, that V being displaced is this shaded purple section and only the shaded purple section. Now, how can I calculate the volume of those? How would I calculate the total volume of the block? Well, I take the length times the width times the height because it's a rectangular prism. And this times the entire height would give me the entire volume. But if I want only the dimensions that are underneath the water, I take the length, because that's underwater, times the width, because that's underwater, times the h, because only that much of it is underwater, and that'll give me my volume that's being displaced. So within that V displaced, we can solve for this h. I want to add one last kind of component to this before we kind of pause, and we'll come back to it on Monday. There's my picture. If we look at this picture and say what forces are acting on this block, hopefully you recognize that there's two. And I'm going to tell you that there's an upward buoyant force. I'm going to tell you that because it's due. I'm going to tell you there is no normal force because it's not sitting on a surface. It's not sitting on the floor. It's not sitting on a table. It's floating in some water. The last thing is there's one more force. And what is that force? Gravity. Okay? And gravity goes straight down. Does the F of G of an object change if it's floating in water? It's kind of a trick question. The answer is no. The weight of an object does not change. If you weigh 100 pounds and you jump in the pool, do you still weigh 100 pounds? Yes. If you jump in the pool and you weigh 200 pounds, do you still weigh 200 pounds? Yes. If I can pick up my 200-pound friend in the pool, does that mean I can pick up my 200-pound friend on land? No. Their weight didn't change. Their F of G is the same. The difference is I have this nice buoyant force in the pool that's helping lift my friend up. That's important. This F of G is the same whether you're floating, sinking, or on land. Your weight is dependent upon your mass and the gravitational acceleration, and that's it. So there's two bits of information that were given. The density of the block, which is 650 kilograms per cubic meter, and the density of the water, which was 1,000 kilograms per cubic meter. I'm not nice enough to give you the mass of the block. Okay? But if I was nice enough to give you the mass of the block, all you'd have to do is say, well, M times G would give me my F of G. But I don't. I do give you, I swear that was a mosquito. That's right. Must be spring. That's weird. I am not nice enough to give you the mass of the block. I give you the density of the block. I give you the total dimensions of the block. And if you know density, and if you know volume, or you can calculate volume, you can then calculate mass. So that's how we'll have to kind of approach this. I'm going to pause on this. I'm going to stop because I want to make sure I give you plenty of time to go through and finish this progress quiz that I have for you. The progress quiz is on pressure, density, pressure at depth, which we've been working on so far. The answers to this are found on that wooden lab table, but on the far side, it's the front and back, so I have one sheet sitting like this, okay, for you to look at and check your answers. Once you finish that, you want to make sure that your homework that is due on Sunday, which is almost identical to this progress quiz, is submitted in Canvas. So, progress quiz, the formulas that you may want to use are on the board right here. You are more than welcome to use your own formula sheet. I don't care, but they are on the board for your quick access as well. Yeah, so when you're done, the answers are on that wooden lab table for you to check. Make sure you get that homework sheet done that's due Sunday and get it submitted in Canvas.